Why is time relative? To answer, you need to know one thing. The speed of light in a vacuum, called c, is constant, which means that whether you're standing on Earth or in a spaceship traveling at 99% the speed of light, you'll measure c to be this much. This has interesting consequences. Imagine standing on a railway station platform with a clock made out of light bouncing off two mirrors back and forth. We can measure time on it, just like a normal clock. We can call the distance between the mirrors d, and it equals c times the time light takes to travel that distance. Now imagine a train passes by, and on that train there's the same clock. From your perspective, light travels a longer distance and it takes a longer time. For people inside though, time is not different. So this means that time as seen from the platform is different from the time inside the train. We measure time inside to be slowed down. But how much? Well, this is a right triangle. And this side is the distance traveled by the train in that time. We can use the Pythagorean theorem, and by substituting our values and solving for the dilated time, we get this equation. This part is called the Lorentz factor, and by using it, we can calculate time dilation. For example, relativistic jets are plasma jets pushed by black holes at velocities near light speed. Let's say that after some time, the velocity is 90% c. By using the equation, we can work out that from our perspective, inside the jet, a clock would tick roughly every 2.29 seconds. We can also visualize time dilation with a spacetime diagram, where 1 on the x-axis corresponds to this much, so that light speed is at a nice 45-degree angle in both directions. Let's say we observe something moving relative to us at 60% c. We calculate that 1 second for the objects corresponds to 1.25 seconds for us. So, we can plot all the other seconds too. Relative to itself, the objects are not moving, so this line is its time axis. With the same angle from below, we find its x-axis. We can see that its spacetime is stretched and deformed. We're doing this deformation so that light speed is the same from both perspectives. From the actual object's point of view, its spacetime is normal, and we are moving in the opposite direction relative to it. It's easy to understand why. If you're standing on Earth and you see a spaceship moving relative to you, from the spaceship's perspective, it's the Earth that's moving in the opposite direction relative to it. What I just explained is just a part of special relativity. It's what Einstein figured out about the speed of light and space and time. It changed our understanding of the universe.